Alright, so this is the review for Chapter 11 on limits and introduction to calculus. So for number 1, we have the limit of that function as x approaches 9. Remember, what we always want to try to do is evaluate the function with direct substitution. But if we try to do that, we notice that if I plug in a 9 for the x, on the bottom I get 9 squared, which is 81, minus 81, which is 0. So I can't use direct substitution, so we need to use some other method, and we're going to start by factoring. So if I factor this, I get the limit as x approaches 9 of 9 minus x over x plus 9 times x minus 9. And now if I do a little bit of manipulation on the top, that top turns into negative x minus 9. So if I just factor out the negative sign from the two terms, I get negative x minus 9, which means that my two factors cancel out of x minus 9, and I'm left with the limit as x goes to 9 of negative 1 over x plus 9. Now at this point I can use direct substitution, and I get negative 1 over 9 plus 9, which is negative 1 over 18. If I look at 1b, same type of problem, same type of issue that we have, which is if I try to plug in a negative 4 with direct substitution, I'm going to get negative 4 plus 4, which is 0, cancels out, can't do it. So instead, I'm going to try to factor the top. The numerator, is going to factor to be, let's see, 2x plus 1, sorry, 2x minus 1, and x plus 4. And I know it's going to be that because 2x times x is 2x squared, 2x times 4 is 8x, minus 1x, it's going to be 7x, and then minus 4. All over x plus 4. And then once again, I have a factor that cancels out, and I'm left with the limit as x approaches negative 4 of 2x minus 1. Now I can evaluate that at negative 4. 2 times negative 4 is negative 8, minus 1 is negative 9. Alright, number 2, we have the limit as x goes to infinity, so we're going to use our other rules that we learned a couple days ago, where essentially we're going to look at the highest power and determine what to do from there. So the first thing I can see that I can do here is that I can combine my like terms. So I've got 3x minus x is 2x over 2x squared plus 4, and that's the limit as x goes to infinity. And now that I have this, I can compare my highest powers, which are 1 and 2. Since the denominator is larger, I know that my denominator is going to increase quicker than my numerator, which means that I'm eventually going to get something like 1 over some really big number, which is essentially 0. So the limit of 2a is 0. Part B, same idea. There's no simplifying that I need to do. When I look at this, I see that both of them are squared. If the powers are the same, I simply compare the coefficients, and I have a limit of 5 over 2. Number 3, once again I'm finding the limit as x goes to infinity. We've got a little bit of work to do here. The top part, the numerator, I don't need to expand it all out, but I know that that's going to turn into essentially, my highest power is going to be like a positive x squared, because it's going to be negative x times negative x, and the denominator is going to be 4x squared. Now obviously there's more to it. If I write the whole thing, I'm going to have x squared minus 2x plus 1 and 4x squared plus 3x. But as we mentioned in class, eventually these aren't going to matter, and so I'm left with x squared over 4x squared. Compare my numerators once again, or compare my powers once again, they're the same. So I divide my coefficients and I get 1/4. Part B down here, I've got x cubed over x squared minus 9. As x goes to infinity, so since x is going to positive infinity, and once again I'm looking at my powers, 3 and 2, similar to number 2, but this time the top is going to grow faster than the bottom. So at some point I'm going to get some really ridiculously large number over something smaller than that, like infinity over 1, which means that this graph just goes to infinity, which tells me that the limit does not exist. Alright, moving on to 4. Find the limit of radical x plus 2 as x approaches negative 1. Again, we're going to try direct substitution. In this case, direct substitution will work. There's no reason why I can't just plug in a negative 1, because negative 1 plus 2 is 1, so I have the square root of 1, which is just 1. So the limit of that function is 1. Part B, limit as x approaches 0. I have an issue if x is 0 because I have a undefined solution. So instead we're going to use one of our methods, which in this case, because I have two radicals, I'm going to multiply by the conjugate, which is radical x plus 3 plus radical 3. Multiply that to the top and bottom. We know that when we do that, the numerator is going to just squaring these two terms separately. So I end up with x plus 3, because radical x plus 3 times radical x plus 3 is x plus 3, minus radical 3 times radical 3, which is 3, all over x times radical x plus 3 plus radical 3. Now those 3's cancel out, and I'm left with the limit as x approaches 0 of x over x times radical x plus 3 plus radical 3. Those x's cancel, so I get the limit as x approaches 0 of 1 over radical x plus 3 plus radical 3. Now I can go ahead and evaluate with direct substitution for 0. If that x goes to 0, I have 1 over radical 3 plus radical 3, which is 1 over 2 radical 3. Alright, 5a. Again, direct substitution is not going to work, because 2 take away 2, I'm going to get undefined on the bottom. Since I have a polynomial here, I'm going to factor this, but factor by grouping is not going to work. It's not a standard trinomial, but we talked about in class that we can kind of cheat because we know what we're trying to get. We're hoping to get a factor of x minus 2 out of the top. So going back to like chapter 3, the only factor we really care about is having a factor of x minus 2, so we can check if that's a factor by using some long division. So I'm going to check if x minus 2 goes into x cubed minus 3x squared plus 5x minus 6. We could choose to use synthetic division here. I'm using long division just because. So if you recall, x times x squared is going to give me x cubed, and we multiply it back through. So I've got x cubed minus 2x squared. We subtract that, those cancel. Negative 3x squared minus negative 2x squared is negative x squared plus 5x. Do the process all over again. I've got minus x here, so I've got negative x squared plus 2x. If I subtract that, I get 3x minus 6, and do the process one more time. 3 times x is going to give me 3x, so we've got 3x minus 6, and the good news is, now I can see that everything cancels out and I'm left with the remainder of 0, which means that x minus 2 was one of my factors of the numerator, and my other factor was x squared minus x plus 3. So I can rewrite this limit as the limit as x approaches 2 of x minus 2 times x squared minus x plus 3 all over x minus 2. And now these factors cancel. And I get the limit as x approaches 2 of x squared minus x plus 3. Now I can use direct substitution. 2 squared minus 2 plus 3. It's going to be 4 minus 2 plus 3. 4 minus 2 is 2. 2 plus 3 is 5. Part B. Part B. We've got direct substitution here. I'm not going to have an issue because 1 take away -1 is 2. So I can go ahead and just plug it in. So I've got -1 squared plus 5 times -1 minus 3 over 1 minus -1. -1 squared is -1 minus 5 minus 3. And the bottom is going to give me 2. So I'm left with -6, -9 over 2. Alright, so number 6. Once again, we cannot just use direct substitution because we get an undefined value. But we have a complex fraction here, so we're going to start by simplifying the numerator. We're going to do some cross multiplication. So I'm going to multiply the left-hand fraction by 8. So I've got 8 plus, now the right-hand fraction we're going to multiply by x minus 8. So it's going to be x minus 8 all over the entire common denominator of 8 times x minus 8. That whole thing is divided by x. And obviously it's the limit as x goes to 0. And so now if we simplify this a little bit, we see that it's 8 minus 8. Those cancel out. So I'm left with the limit as x goes to 0 of x over 8 times x minus 8 all over x. We know that those x's are going to cancel, and we get the limit as x goes to 0 of 1 over 8 times x minus 8. Now we can use direct substitution. Direct substitution, I'm going to plug in a 0 for x, so I get 1 over 8 times 0 minus 8, which is going to be 1 over 64. Part B, same idea. Can't use direct substitution, so instead I'm going to simplify my fractions, multiply the left-hand fraction by 4. So the limit as x goes to 0 is going to be 4 minus, I'm going to multiply the right-hand fraction by 4 minus x, and get a common denominator of 4 times 4 minus x all over x. I'm going to distribute that negative sign. 4 take away 4 cancels out, and I'm left with the limit as x goes to 0 of x over 4 times 4 minus x all over x. Those x's cancel. Limit as x goes to 0 of 1 over 4 times 4 minus x. Once again, now I can do my direct substitution, make x go to 0, and I get 1 over 16. 7. We're going to take the limit as x goes to infinity. Since we have a sum, we're going to split it apart. So we mentioned in class that we can use our limit property. It says that we can write this as the limit as x goes to infinity of 7 plus the limit as x goes to infinity of 2x squared over x plus 3 squared. The limit of 7 as x goes to infinity is obviously 7 plus. In the second limit, we compare our powers. I've got squared, and this will eventually be squared as well. So I compare my coefficients, and I have a 2 and a 1. If you need to expand it out, you can. 2x squared over x squared plus 6x plus 9. And we can see our lead coefficients. So I get 2 over 1, which is 2, which gives me a limit for the function of 9. Part B. This is going to be similar to one of our previous problems. So we're going to start with looking at what happens when we try to expand this. So this guy turns into x squared plus 6x plus 9, and then you're going to multiply it by that negative x. So we're left with negative x cubed minus 6x squared minus 9x all over 2 plus x quantity cubed. If I expand that all out, I can do the whole expansion, but all I really care about is that lead coefficient, which we can see is a 1x. Eventually that's going to get cubed, and I'm just going to be left with x cubed. So now we have our greatest powers. So x cubed plus stuff. So we've got our greatest powers, which are the same. So we divide our lead coefficients once again. We've got negative 1 over 1. Since we're going to positive infinity, x cubed is going to stay positive, x cubed on the top is going to stay positive, and I just look at what's negative 1 divided by positive 1, and I have a limit at negative 1. 8. So we have the limit of a piecewise function. We remember the definition of a limit was that we can find the limit of each half, like the left-hand limit and the right-hand limit, and compare them. If they're the same, then the limit exists. If they're not the same, the limit does not exist. So since we have a piecewise function, I can plug the value of 2 into both the top function and the bottom function, see what happens. If they match, we have a limit. If they don't match, we don't have a limit. So first I'm going to check the limit as x goes to 2 from the negative side, which would be 8 minus x squared. I can use direct substitution, so I get 8 minus 2 squared, which is 8 minus 4, which is 4. I'm going to separately check the limit as x goes to 2 from the positive side, which is going to be the x plus 2 function, which is going to be 2 plus 2, which is 4. Since the left and the right hand match, the limit of my entire function is that value, which is 4. Part B, same thing. I'm going to check the left-hand limit, so x approaches 2 from the negative side. That's going to be this negative 2x. So that's negative 2 times 2, which is negative 4. And I'm also going to check the right-hand limit as x approaches 2 from the positive side. That's going to be the bottom function, which is going to be x squared minus 4x plus 8. Direct substitution. I've got 2 squared minus 4 times 2 plus 8. 2 squared is 4, minus 8, plus 8. Those cancel out. I'm left with just a positive 4. Since my left side and my right side are different, the limit does not exist. Alright, number 9. So sketch a graph that has the following properties. So we have to make a graph. There's a bunch of different correct answers. I'm just going to show one possible correct solution for this. So it has to meet each of these 4 parameters. So f of negative 2 has to be 5, f of 3 has to be 2, the limit as x goes to positive infinity has to be negative 2, and the limit as f of x goes to, or as x goes to 3 cannot exist. So let's start with the 2 easy ones. Remember that notation says f of x equals something. That means that when x is negative 2, y is 5. So that's like saying there needs to be a point at negative 2, 5, and there needs to be a point at 3, 2. So at negative 2, 1, 2, 3, 4, 5, there should be a point there. And at positive 3, there should be a point at 2. Alright, so that satisfies the first 2. Now I want the limit as x goes to infinity of the function to be negative 2. So that means that at some point, here's negative 2. So as x gets really large, so as I'm all the way over on the right side of my graph, all the way over here, my function needs to be approaching negative 2. Well, the easiest thing to do is draw a graph that kind of curves down and shows that it's approaching that line, that horizontal line of -2. So now I've taken care of this part. I can see from the graph that as my graph approaches positive infinity, I follow this line, and my function approaches that value of -2. Alright, and then the last part, I want the limit of the function as x approaches +3. So +3 is this line. I want my limit to not exist. Well, if it doesn't exist, it means the left side and the right side don't match. Well, one of the two sides, it appears to be the right side already, if we follow that line that we just made, approaches the value of +2 at this point. Okay? So I need the other side to not approach this value. You can go anywhere else, just not here. So I might have it go, I'm going to draw like an open circle right above it. And actually, I might go a little bit higher, like up here. So now we have two different values, and then all I have to do is draw some sort of a graph that goes away from that. So when I look at this graph, the value of f of -2 is 5. That matches the first one. This point here is f of 3 is 2. Then the limit as x goes to infinity is -2, so we have that down here. And then the limit as x approaches 3 is not defined, and we see that because here's x equals 3 is this vertical line right here through +3. The left side of the function approaches +4. The right side of the function approaches +2, so the limit does not exist. Alright, 10 through 25, we're going to use those graphs. So I'm going to shrink this down just a little bit. So starting with number 10, f of 2. f of 2 means find the f function, evaluate it at x equals 2. So here's my f function. When x is 2, I go up to my graph. What's my y value? It's 2. 11, find the limit of the f function as x approaches 2. So I'm going to look at, here's that vertical line, x equals 2. And the limit, I have to check the left side of the graph and the right side of the graph as they approach that vertical line +2. So from the left side, my graph approaches that same dot of +2. From the right side, my graph also approaches that same dot of +2. So my limit is 2. Number 12, g of -1. Well, here's -1. There's an open hole there, so that means that it is undefined. There is no value for the function at -1. Undefined. 13. What's the limit of the g function as x approaches -1? So this is where I use my limit definition. As x gets close to that value, that vertical x value, x being -1, from both sides, what does the graph appear to be approaching? From the left side, if I trace the graph, it's approaching the value of +1. So the limit as x approaches -1 from the negative side is 1. I also need to check the limit as x approaches -1 from the positive side. So from the positive side, that's the right side, so I'm following this side of the graph, and it's approaching that same value of +1. Since the left and the right side match, the limit is 1. 14. What's h of +1? Well, +1, there's this vertical asymptote. The left and the right side don't have a value, so once again, I am undefined. The limit as h of x approaches +1. Well, the left side of +1, so I follow this graph, it goes up, and it goes up infinitely to infinity. The right side also goes up infinitely to infinity, so we are not defined. Again, the limit does not exist. 16. J of -2, so I find my j function, find x equals -2, and when I look at the graph, I have another vertical asymptote, so my function is undefined. And once again, the limit of j at -2, the left side of -2 goes to positive infinity, the right side of -2 goes to negative infinity, so since the two sides don't match, the limit does not exist. 18. K, the limit of the k function as x approaches 2. So once again, I have to use my limit definition. I need to check the limit as x approaches 2 from the negative side and the limit as x approaches 2 from the positive side. So here's positive 2 right along that path. From the negative side, we're following this line and my graph approaches -1. From the right hand side, my graph approaches +1. So the limit from the left is -1, the limit from the right is +1. So the limit does not exist because these values do not match. 19. The limit of k of x as x approaches 2 from just the positive side. So we're just going to look at the right side of the graph, which is going to be over here. My graph approaches the y value of +1. 20, m of 1. So here's the x value of 1. There's an open circle at the top of my function, which means it's not defined there, but there's a closed circle down here. This is where my function is defined. So the value of this function at 1 is whatever y value we have here, which appears to be -3. 21. What is the limit of m as x approaches 1? So once again, the limit, it's not what the function is equal to, not what the graph is equal to, but what it appears to be approaching. So I check as x goes to 1 from the left side and as x approaches 1 from the right side. From the left side, I follow my graph and it goes up and it appears to be approaching whatever y value this is. From the right side, it's also approaching that same y value, which both sides are 2. So since the left side and the right side approach the same value, the limit of my function is that value, which is 2. 22. What's the limit as k approaches -2 from just the positive side? So I'll find my k function here is -2 for the k function. So again, from the positive side of -2, that's going to be the right side. Our value is approaching -2. 23 is the same as 11. Same limit, it's just 2. 24, what's the value for k of 2? So for k of 2, I find the x value 2. There's a closed circle down here at -1. There's an open circle here, +1. The closed circle is the value of my function. So my value for k of 2 is +1. Remember, those are y values, those are outputs. 25. What's the limit of k as x approaches 2 from the left? So once again, here's 2. As x approaches 2 from the left-hand side, we're following this line, which puts us at -1. Alright, 26. So find the slope of the function at 312. So there's two ways we can do this. I'm going to start with the more difficult way, maybe not more difficult, but the way that we originally started the problem in class. And remember, slope was the derivative, and our definition of a derivative was the limit as h goes to 0 of f of x plus h minus f of x all over h. We know what x value we want to evaluate it at, and we have our function. So if we just plug stuff in, the limit as h goes to 0 of f of x plus h, so wherever I see an x, I'm going to replace it with x plus h, or in this case 3 plus h. So we got 10 times 3 minus 2 times, sorry, not 10 times 3, 10 times 3 plus h minus 2 times 3 plus h squared minus f of x, which is 10x, but we know that x is 3, so 10 times 3 minus 2 times 3 squared, and that whole thing divided by h. Simplify this a little bit. Limit as h goes to 0. I've got 30 plus 10h minus 2 times 9 plus 6h plus h squared minus 30 plus 18 all over h. So it's the limit as h goes to 0 of 30 plus 10h minus 18 minus 12h minus 2h squared minus 30 plus 18 all over h. And we've got some canceling that we can do. 30, -30, -18, +18, 10h, -12h, and -2h squared. And then the h on the bottom, we can cancel a single h out of each of those. And I'm left with the limit as h goes to 0 of 10 minus 12 minus 2h. Now I evaluate that as h goes to 0, so this term goes away, and I just get 10 minus 12, which is -2. So that's the long way. The short way we talked about in class, the shortcut for derivatives, which was, since this is a polynomial, we could use our rule of if f of x was a x to the n, f prime of x was a n x to the n minus 1. So f prime of x is going to be 10 times 1, which is 10, x to the first minus 1, so 1 minus 1 is going to be 0, so I just get 10. And then I do the same thing for the second part. -2 times 2 is -4. X to the first now, because I reduced the exponent by 1. So this is my general equation. Now if I plug in a 3, I have 10 minus 4 times 3, which is 10 minus 12, which is -2. So we get the same result either way. It doesn't matter how you do it. Alright, and then the very last problem. Once again, find the slope of that function when x is equal to 5. This one, because it was a radical, we didn't have a shortcut for that, at least not one that we have learned yet in this class. So we need to find the slope of that. So we're going to use our limit definition. The limit as h goes to 0 of f of x plus h minus f of x all over h. We know that x is 5. So if we start plugging stuff in, I have radical 5 plus h minus 2 minus radical 5 minus 2 all over h, which is the limit as h goes to 0 of radical 3 plus h, when I simplify, minus radical 3 all over h. We now have a complex radical problem, so I'm going to multiply by the conjugate 3 plus h plus radical 3 over radical 3 plus h plus radical 3. And I get the limit as h goes to 0 of 3 plus h minus 3 all over h times radical 3 plus h plus radical 3, which is going to be the limit as h goes to 0 of, we cancel the 3's, cancel the h's, I get 1 over radical 3 plus h plus radical 3. Evaluate this as h goes to 0. I get 1 over rad 3 plus rad 3, which is 1 over 2 rad 3. That is the slope of my function when x is equal to 5. That's going to do it for the Unit 11 practice test.